Alrighty, welcome back ladies and gentlemen. We're talking 6.4 day 2 now of vectors and dot products. Okay, what we're going to be doing today is determining the relationship between vectors and using dot products for some physics applications. Alright, now vector relationships, and just like lines or segments, there's really about two relationships that we worry about in general, and those are perpendicular and parallel. The only difference now with vectors is we have a fancy word, orthogonal, that effectively means perpendicular. Okay, so don't let that throw you. Okay, now vectors u and v are going to be orthogonal, which again, perpendicular if, and again we're going to capitalize on our dot product sort of stuff, is if we take the dot product of u and v and we get 0. Okay, I'll demonstrate why that's true in an example real soon. Or of course we can be parallel. Okay, vectors u and v are parallel if, well, this one's not too much of a shock I hope, if their slopes are the same. Okay, so we're still going to be using the whole rise over run thing, but if you think about the component form, that's basically all they're doing is they're showing the rise and the run. Okay, and again, for vectors to be equal, they have to be facing the right way, but for parallel, they don't have to be facing the right way, so that's why you can be facing opposite directions here. So just again, calculate the slope, and as long as those slopes are equal, your vectors are parallel to each other. Alrighty, now, just like in the days of Algebra 1, or whenever the first time it was you saw that, and you were given two segments and asked if they were parallel, perpendicular, or neither, and that's exactly what we're doing right here. Just we have another way we can test it now. Alright, well, again, looking at the vector u, which is 5, 6, so again, that just means I'm going right 5 and up 6, and then the vector v, which means I'm going left 12 and then up 10. Okay, are those guys going to be orthogonal, perpendicular that is, parallel or neither? Okay, now there is some manner of common sense that you can apply to this stuff. For instance, if this guy's going right and up, okay, he's got kind of a positive slope. This guy's going left and then up, he's going to have kind of a negative slope. So clearly these guys aren't going to be parallel. Okay, so right now it's basically orthogonal or neither. Alright, so basically again, I'll do my dot product, u dot v, okay, and my dot product is going to be 5 times negative 12 plus 6 times 10, and hopefully not too shockingly, negative 60 plus 60 gives us a 0, and by that sort of theorem thing we did a little bit ago, that means these guys are orthogonal. Which again just means perpendicular, and again just to demonstrate why this works. Again, if you take a look at u, again the 6 is your vertical move and the 5 is the horizontal move, so basically the slope of u is basically 6 over 5. And then doing the same thing with vector v, the slope of vector v is really 10 over negative 12. And by doing a little reducing and then let that negative sign move up to the top, basically what we get, reducing by 2, is negative 5 sixths. So again, that's basically all it is just showing that, hey, if I do the dot product on vectors that have that sort of relationship, I get a 0, so it's orthogonal, but again, it just really means perpendicular. Alright, moving to our second example here. Okay, I've got this sort of thing, and again, if I've got a negative move here and a positive move here, negative is left and then positive is up, so I have a negative slope on this guy. And then right and down is also a negative slope. So right now I know these guys aren't orthogonal. So again, it's just, hey, are this parallel or neither? So since it's not orthogonal, the dot product doesn't do me much good, so I'm going to go right into the slopes. So the slope of u is, again, 15 over 10, negative 10 actually, and then I'll reduce that into a negative 3 over 2. And then my slope of v, again, this is my rise, negative 3, and then the 2 is the run, so 2. And there you go, these guys are parallel. Okay, I'm skipping an example where you get neither, but basically, if you don't get one of these others, then, well, it's neither. Okay, hopefully that makes a little bit of sense. Alrighty, now, work is a concept in physics, and work is equal to force times distance in physics, so just force times distance. Okay, now, there's a few different ways of figuring out force in physics, but we're not going to go there, at least yet, or at all. Okay, fine, I won't do it at all. Anyway, using vectors, the work W done by a force F. Okay, now one thing to notice here, that is bold, so this is going to be a vector. So we need a vector to represent our force as it moves along a vector D, which is distance, but again, since it's a vector, it's also kind of implying a direction of sorts, and is given by this right here. I've got work equals force vector dot product with our distance vector. Alright, that's going to generate the amount of work done by anything. And let's take a look at a couple examples of that. Alrighty, so where work comes into play is finding the work done by a crane lifting a 3,000 pound truck 15 feet vertically, so maybe it's got to load it onto a ship or something like that. Okay, so anyway, again, working with what we just had, our work is going to be the force vector dot product with the distance vector. Alright, so basically what's going on here, okay, so it's maybe not overly clear, but since vertically is what's happening, I've got my crane, whatever it is, and draw something that looks very, very uncrane-like, but looks like playing Hangman more so. But anyway, let's pretend that this is a crane over here, and it's reaching down here and picking up a truck. Wow, look at that aerodynamic truck. It looks like a Batmobile. Okay, well anyway, whatever my truck looks like, okay, this crane right here has got to lift up the truck 15 feet. So it's going to go 15 feet there, and it's a 3,000 pound truck. Okay, well the 3,000 pounds is effectively our force. Okay, it's the force that's the crane is acting against to lift, and then of course the 15 feet, hopefully that makes a little more sense to the distance. So basically what I want to do is look at these two vectors as their components, and I'll admit this one's going to be a little bit easy because everybody's going all in the same direction. Okay, so my force, okay, I want to lift that truck vertically. So I'm not applying any force in a horizontal direction, but I'm applying 3,000 pounds of force in a vertical direction. And the distance vector is exactly, well, not exactly, but very similar. Okay, the distance I'm going vertically, so again, so I'm not doing any sort of horizontal movement, so I have a 0 there, and then I'm going 15 feet up, so there's your positive 15. Alright, so work is the dot product of these two guys. So it's 0 times 0, get a calculator for that one, plus 3,000 times 15. Alright, and after a little bit of number crunching right there, we get 45,000. Okay, and 45,000 what? Well, 45,000 foot-pounds. Oops. Okay, work is measured in foot-pounds in the English system, which is almost a little bit backwards of the formula because distance is feet, and then that unit goes first, and then the force is in pounds, and it goes second. For those of you who care, there is something called a pound-foot, but that applies to something called torque. And if you're not sure about that, we can talk about it in class a little bit. But anyway, there you go. Alright, let's take a look at this in a kind of more generic point of view. Okay, let's pretend we're moving a particle from some point P, which is at negative 2, 1. So negative 2, 1 right there is where P is. And then we're going to Q, 3, 0. Right. Okay, now one assumption I sort of have to make here is that there's got to be some kind of direct path between the two. Because we're not specifying it's got to go up over some hill or down in some valley or something like that, so we're going to have to make a little bit of an assumption here that there's some very direct route straight from P to Q. Okay, and again, I'm going to think of that as a vector because it happens to fit the formula we're trying to use very nicely if I do. Alright, now the force is moving along 4I plus j, vector v. And again, the vector is just a directed segment basically, so I can put him anywhere I want. I mean, I could put him at the origin right now, but I think that looks kind of crazy what's going on. So let's put him right here. Okay, so here's my vector v, starting here at least. And if I go 4 units to the right and 1 unit up, that's what v is looking like. Okay, so there's vector v. Okay, now, so basically I'm going downhill and I'm pulling this. And if that doesn't make sense to you, well, just imagine some little kid pulling a toy on a string. Okay, so the kid's holding the string up here, and then the toy's on the ground, and then he's walking down the hill. And that's basically what's happening here. So as this child is pulling this toy down the hill, how much work is getting done? So little kid's going, ooh. Alright, anyway, here we go. Alright, so again, I want to think of the two vectors I have. Now the force vector is, well, the force along v, so it's pretty obvious which force is the, which vector the force is. Alright, so anyway, work equals, okay, and again my force vector, okay, this is pretty easy to think of as a component form because it's 4I plus j, so it's the same thing as saying 4, 1. Okay, my distance vector is not quite as easy, but now that I have a graph, it's not so bad. Notice here we're going 5 horizontally and then 1 down. So this is 5 comma negative 1. Alright, so there's our two vectors, and again, just doing the dot product is 4 times 5 plus 1 times negative 1. So basically I have 20 minus 1, so the work is 19. Now granted here we don't have any units to work with, so I'm just going to stop at the 19 and not try to label it. But anyway, there you go. Alrighty, let's take a look at one that's a little more real world. Alright, it's got a tractor pulling a log 300 meters, and the force is 40 degrees above horizontal, and I got the tension of the cable is 800 kilograms, so I know it'll work. Okay, so there is no specification about horizontal versus vertical, well actually going uphill or downhill, let's just do it that way. So pretend I made a straight line there, let's pretend that's horizontal, and then I got my log right here, put some nice wood grain on that thing, and some little tree rings, beautiful. Alright, so again, I got some tractor that's going to be pulling it, so I'll put a big old tractor tire there, and let's put a seat right there, put some guy sitting on top of here, looks like Farmer Brown to me, I'll give him a hat. Alright, so he's steering it right there, and tractor usually has a little wheel in the front, so anyway, something like that, pretend it's a tractor. Okay, and I've got my cable right here, and that cable, relative to the horizontal, is 40 degrees up. Okay, and what we want to do is we want to take this guy 300 meters. Let's make that 3 a little nicer. Alrighty, so basically there's our scenario. He's dragging a big log out of the way or something, and let's go. Okay, so I want my work, again, is going to be the dot product of force and distance. Alright, so I need to come up with a force vector and a distance vector. Well, the distance vector in this one is going to be pretty simple. My distance vector, well, I'm going horizontally 300 feet, and I'm not going vertically at all. So there's my distance vector. Okay, the force vector is a little more complicated. Okay, so for force, okay, well, first thing first, let me kind of pull that triangle out, maybe make them a little nicer to see. Alright, so here's my 40-degree angle, and the tension here is 800 kilograms. Alright, and basically if I want my component form again, because that's what I need to do a dot product, I've got to figure out my force in the y direction and my force in the x direction. Alright, okay. And the good news is, since I'm dealing with horizontal versus vertical, I have a right angle and I can use SOHCAHTOA. Alright, so that being said, basically my force in the x direction and simply be basically it's cosine equals cosine of 40 equals f of x over 800, and a little bit of simplifying, solving the equation if you will, gives me 800 cosine 40 degrees to be the horizontal component, and then for the y component I'd use sine, so sine of 40 equals f sub y over 800, and again I can sort that out into 800 sine of 40. Okay, so basically my force vector f is going to be 800 cosine 40, which gives me a decimal of roughly 612.83, and again dot 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 because it keeps on going. And then in the y component I end up with 514.23 dot dot dot. Okay, so now I've got my d and I got my f, so I can do my dot product. So now work is my dot product here. I've got 612.83 dot 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 times the 300. Okay, and admittedly this next half is a little bit silly because I've got the 514.23, and honestly I don't care because I'm going to multiply that guy by 0 anyway. Alright, so basically all I have to do is take the 612 times 300, and that works out to be 183.85, and then something that rounds up to a 1. Alright, so that's how much work is being done. In the metric system, if this is foot-pounds, then this ends up being meter kilograms. Okay, although I confess, I'm not 100% sure if that's a good unit of measure in the physics world, so quite honestly I'm more concerned with you getting the number than I am with you putting the appropriate units on there, so I'm not even going to circle the unit, ha 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 ha. But anyway, there you go, that's how that would work. Break it into components, use a little bit of trig if necessary, and then do your dot product again, should get you straight to the answer. Alright, there it is. Hopefully again it made a whole lot of sense, and I'll see you in class if you got any questions.